All right, everybody, welcome. Tuesday night again. And I see there are already a lot of folks here. Good morning, Thought, and Mavrika, as well as Asha and Igor is here. Excellent. Good to see you, Igor. I don't know if Jason and Loretta are around, but so it's great to see everybody here this evening. I can't actually see you, but you know what I mean. We're going to talk about polarity because we kind of get to this point in the semester where everybody's a little bit kind of getting stressed. Not only the students, teachers get a little stressed out too with all that grading and all that. So do take time to make sure the stress doesn't affect you too much because it will make it harder to remember and harder to retrieve information. So hopefully we can lower your stress here with some polar and non-polar chemistry. And I see Nick's here. All right, Nick, Hector, Connor, Caleb. Caleb made it finally. Excellent. And Junsu Yoon. Excellent. Good afternoon. It's actually evening here. I think we have different time from all over the place here. So let's do this. We'll take a look at polar, non-polar. Then I will show you this really cool free app that you can impress your friends and your teachers with to show really the surface of that polar molecule. And then I'll give you some notes. We'll do a demo. So it should be fun. And there's Zero Motivation is there. Excellent. 11:30 where you're at. All right. Let's kick over to my screen. Here we are. And so I'd like you to see if you can tell me what molecule this is, what it looks like, and if it's polar or non-polar. And this is the app I'm talking about. Hello, Arya and Belaki. Nice. Yoski Broski. Nice. So this is the molecule. What is this? And this is kind of a neat app because you can turn this all over the place. I don't know. This bipolar molecules. That's interesting. I've not thought about it. The red is the oxygen. That's true. Part of it, Mavrika, is non-polar. You are correct, but part of it is polar. So let me show you this molecule here in 2 dimensions, and you can tell me what it looks like to you. So I go up here, and we'll do 2D and 3D. The molecule does need therapy. This is the molecule. It's called nanokid because it looks like a kid. So the actual molecule you can see here, here's the 2 oxygens right here. Here's your benzene rings right in the middle. Oh, excellent, Hector. So we'll learn some stuff. So when we look at whether a molecule is polar or non-polar, we're going to look at the differences in electronegativity. So we'll get to that in a minute. But I wanted to show you our nanokid here, which kind of blows my mind that chemists actually built this. They can build molecules that look like this. And that's pretty crazy if you think about it. So here's how they build it. They started with 1,4-dibromobenzene. They used different chemicals. They kept adding different pieces and different substances until they had the top of our nanokid right here. Then they built the bottom with all these organic reactions. And they put them together with this stuff here. And that's your nanokid. So that's kind of crazy that as chemists, we can build molecules. And if you think about pharmaceuticals, materials for spaceships, anything, we're pretty good at building stuff. So hopefully this will help you get along with all of this. So let's see if it's polar. All right. We're going to go up to JMOL. In a minute, I'll give you the link and you can try this. And we're going to go to the surface, MEP surface. And watch what happens. Now we can see the surface of the molecule. And when we look at the surface of this molecule, let me go here so we can see the whole molecule. Go back to 3D. And then shrink it down. The areas where it's really blue are positive, and where it's really red are negative. So now the green, that's non-polar. Like Mavrika was saying, we talked about polar. Element number 3, is it lithium? The green's non-polar, but the polar, that's right here. That's the blue, that's positive, and the red is negative. So it's both, it is a bipolar molecule. This part's non-polar, this part's polar. So I guess we figured it out. All right. So let's see how you can tell these different compounds if they're polar or nonpolar. Because when you're doing chemistry, this has a lot to do with solubility. It has a lot to do with hydrogen bonding, intermolecular forces. All of that stuff relates back to our polarity here. So let's do that. All right. And we actually have more people on this stream right now. We've broken our record for concurrent views. That's pretty awesome. 31. Wow. We're making progress. All right, so here it is. So this is the water molecule. And here's what you need to know about polarity. Hector, you have the test tomorrow, right? So when we have something like oxygen here and hydrogen here, here's oxygen over here, and here's hydrogen. There's a pretty big difference in polarity, or electronegativity. The oxygen is more electronegative. So the electrons are around the oxygen, and that makes this part of it negative. And if this part is negative, this is going to be positive. So now we have poles. We have a negative pole and our positive poles. So when we're talking about electrolysis and ions, we're probably talking about ionic compounds. So then that's the electronegativity is so big we don't even call them polar, we call them ionic. So it's even more, it's like superpolar. Here we're dealing with all nonmetals. All right, so that's the big thing. Unequal sharing, and it's these electrons between atoms that aren't shared equally. So if you know that, you know a lot about polarity already. All right, let's go down and let me copy this in here to the chat. If you want to go there and try MoleView for yourself, give it a try. And if you, as a teacher, like if a student came to me with a picture of, on their phone of NanoKid, asked me what it was, and then showed me the polarity, I would be like very impressed as a teacher. So if you want to impress your teachers, that's one way that you can do that there. Valence electrons for transition metals are challenging there. I do have some videos on that. If you search my channel for valence electron transition metals, you'll find some videos, but it's a little bit tough. All right, so here we go. Two big factors. One is that difference in electronegativity, and then the shape of the molecule. So these two things, 1 and 2, that's what determines whether we have a polar molecule. And for electronegativity, you should know that fluorine is the most, and in any direction away from fluorine, electronegativity decreases. So that's the trend. That's a good trend to really hold on to. So which one of these is the polar molecule? See if you can figure that out. And zero motivation, you're correct. Organic molecules, especially like lipids, fats, they have a polar end and a nonpolar end. And that allows them to dissolve in both water and in nonpolar substances. So our cells have a lipid bilayer around them just with that type of polarity. Yapper. Okay, there we go. Japanese. All right, guys, don't start with this. All right. So if you're looking at this, you could look at the difference in electronegativity, and you could see right here, we have a pretty big a difference in electronegativity between the carbon and the fluorines. So the bonds, these are polar bonds, and you can draw the dipoles just like that. So the bonds are polar. So we got that. Here, it's not as big a difference, but we don't have this, we have a very different shape. This is not symmetrical. So because it's not symmetrical, this is our polar molecule. Because we have this negative up here and then these down here that are different. So you can look at the bond polarity, but then you have to look at whether it's symmetrical or not. Let's go over to MoleView and look at that. So what do we have? So for MoleView, you type up in here what you're looking for, CH3F, right? That's what we were looking for. And we're going to look at the surface. So then you go up here to JMOL, click on the surface, and then you can see you can see that polarity there. If we can shrink it down some. Here we go. See how the top is really red and the bottom is blue? That's because the electrons are more around the fluorine, less around the hydrogens. So the electrons in this bond right here. So definitely CH3F, that's your polar molecule. So you can use something like this to figure that out. All right. So let's do this. Let's take a look at hydrogen bonding, because Zero Motivation was interested in that, and I'm interested in that as well. I want to show you a demo, though, first. So let me see if I can set this up here with my camera. See if it works. It may work, it may not. And then, yeah, so we're looking at a beaker of water right here. So you're looking right down on a beaker of the water. Hello, Nishit. I'm saying it right, Nishit. And what I'm going to do is I'm going to float a paper clip on the water. The water molecules are all hydrogen bonded to each other. And what's happening is they kind of form a web or a net of water molecules. So we can actually take, and we should be able to float a paper clip on the hydrogen bonding. Those water molecules, they form like a net. So here's the paper clip. I have it on a fork. And I'm just going to kind of slowly put it in here. Oh, it's holding on to my fork. Don't hold on to the fork. There we go. And there's a paper clip just floating on the water. And that's pretty crazy to think of this piece of metal as just on top of liquid water. And it'll float there. It won't even rust because it's not really in the water. It's on top of the water. So it won't even rust, which is kind of cool. So you could leave it there for a few days. It wouldn't rust. That's hydrogen bonding. If you don't have a fork, because not everybody carries a fork around, right? You can take a piece of tissue paper and make like a little hammock for it. Sometimes this works. And then just set the tissue paper in there. So right now it's resting on tissue paper. And you can float the paper clip like that. And you can even see the way it's bending the water a little bit. You don't have a fork in your country. You have to use some tissue paper there to do that. All right. Okay. So what I'd like to do then is I'm going to go back here. Oh, that's where I'm at. I'm going to go back to my screen and I'm going to show you why that hydrogen bonding works. What's really happening there to make it work. So if you understand this, you'll actually be able to do quite a bit of, this always comes up on exams. Teachers just love this. So we're going to take the water molecules. The red's the oxygen, the white, the hydrogen. Think about how just these two water molecules, how would they line up with each other? So in your head, how are these going to come together and line up? It might help if we write in the negative here, and then this side's positive, positive, and a negative like that. Think about that. So I'm going to take these, group that together. All right. So remember, positive and negative are going to attract. All of the blue touches, that wouldn't work because the blue's positive, right? So if the blues touched the positives because they're alike, they'd push away. So it's actually all of the oxygens. I'm not sure. Oh, I'm squishing that there. Let's see if we can do it like this. Think of the pluses and the minuses all lining up like that. Dipole-dipole interaction. It is definitely that. And then this one over here, it might come and I don't know, maybe it'll go up like this here a little bit. And they are connecting a lot like magnets. It's not magnetism, it's electrostatic attraction, but it still is very much like magnetism. And then this one over here, maybe it would spin like this here. So it might line up there. And then this one could line up maybe like that. And when that happens, right, opposites attract, you got it. And there is a lot more to this. You have to think about your lone pairs and stuff. So you get these weak hydrogen bonds like this between the atoms. They're very weak, but they're enough to really support that paperclip in there. So hydrogen bonding comes up because we've got polar molecules. We have a positive and a negative, and they can kind of stick together. That's pretty cool. All right. So if you know about hydrogen bonding, hopefully that'll help you as you come up against that on some exams here. Let's see this. I think what I'd like to do is, my camera's a little off. It makes me look short. There we go. I want to go back over to MoleView, and you might want to go into MoleView yourself too. Let me put that back in the chat for you. Where's that at? You can give this a try yourself as well on MoleView here. Let's look at a molecule of, say, caffeine, because everybody needs some caffeine, right? I know I need some caffeine right now. So I type in caffeine, E-I-N, yeah, or you can spell it either way, I guess. And here's the caffeine molecule. And it's this part right here. This is the active part. This is what gives you the physiological effects right here. And so I'm going to go up to JMOL and put the surface on. Before I do that, think about what's going to be polar and nonpolar here. Woke Veggie, I think some of the things about water, it's not so much that the hydrogen bonding makes it take the shape of the container. It's like if you look at a water drop, it'll kind of have like a domed shape. And that's because the hydrogen bond's holding it together, or my paper clip that's floating. So alcohol has some hydrogen bonding, but not quite as much, and it takes the shape of the container too. So it's not really that hydrogen bonding makes it flow as much. It kind of makes it stick together is the way I think about it. All right, caffeine. So this is what keeps us awake. We're going to go look at JMOL and the surface. And you see all this red and blue. The blue's positive, the red's negative. And this is really cool because when you think about your cells, receptors in your cell and in your body, not only does the shape, kind of like this, a little bit flat, right? Not only does the shape matter, how it fits in receptors, but the polarity matters. Because if the blue and the red doesn't match up with your receptor's polarity, it won't fit. So a lot of this polarity has to do with how drugs interact, how biomolecules interact. It's kind of fascinating stuff. And like a pharmacist would look at polarity and shape all the time, and any biochemist would. Caleb, you're always trying to convert molecules into different molecules. I like that. Glucose and sucrose aren't the same. Glucose has one ring, sucrose has two. And thank you. I'm glad my voice is soothing. I always wonder about on this mic here. All right. And you're right, Zero Motivation, that water boils at a much higher temperature because the molecules are sticking together. They're bound together through hydrogen bonding. So that's why water boils so high, is because the molecules are hard to break apart. All right. I'm not sure what molecule that is, Mavrika. I'm going to call that a organic molecule, and it may be that it could be a number of isomers. And Caleb, you're right. You can break down sucrose into fructose and glucose. Those are the two rings. All right. So if anybody have any molecules you want to look at in MoleView, what's a good molecule to look at in MoleView? How about DNA? I wonder if they have DNA in there. Let's see what they do with DNA. No problem, Connor. Oh, here's DNA. So watch what it looks like. I'm going to turn it. That's what you're used to, but if you look at it down the middle, that's what it looks like. So in this program, in MoleView, you can also look at different things like proteins, different ways to look at proteins. So you could look at DNA. I don't know if it's going to let me do much more here. Doesn't seem to let me do much here. You can look at different representations and so on. Pretty cool stuff. Yep, C6H12O6 is glucose. Correct. Yeah, anytime someone writes a formula, Caleb, I mean, there may be isomers. If I just look at the formula, I can't always figure out what the molecule is going to be. How about we look up, I don't know. I can't think of a good molecule. I usually can think of a good molecule. I like water, you know, and water, there's a number of different ways you can look at water here too. But this is the one thing, if you go in here and play with water, it'll really help you understand what it looks like, why it's polar. And you can even do stuff like clear this. You can look at the dipole. So if you look at the overall dipole, you can see it goes right through there. Yeah. So, oh, dopamine. Yeah, thank you, Zero Motivation. What do you think the dopamine molecule looks like? I bet it's not that big. Yeah, it's not that big. It doesn't, you know, initially it doesn't look that different than caffeine. It has nitrogens and oxygens. So is dopamine polar or non-polar? That's an interesting question. I think it's pretty obvious. If you've got a bunch of oxygens here, let's look at the surface. Yeah, that's a pretty polar molecule. Look at the blue here and the red on each side. So this would dissolve in water because water's polar and dopamine's polar. So this would dissolve in water pretty well. Alpha and beta glucose. Let's put glucose up there. G-L-U-C-O-S-E, glucose. So there's glucose. You can see the one ring. So glucose dissolves in water pretty well. And here's why. Look at all that red there. So the water molecules, they can all line up around it and pull it apart, and not pull it apart, the bonds, but separate the molecules of glucose. Let's look at sucrose. So sucrose dissolves in water. Is it going to be polar or non-polar? Whoa, look at that. It's a little confusing, so I'm going to go to... let's look at the 2D here. So that's a little easier to understand than this. You can see a ring here and you can see a ring here, but they're kind of bent weird. Yeah, so let's look at this. Is this polar? Absolutely. This is pretty small for an organic molecule. That's a pretty polar looking molecule to me with all of that. So I'd recommend that you go to MoleView and look at some of these molecules so you can look at them here. If you look at them in 2D first, think if they're polar, then go over to 2D, 3D, make sure you have the surface on, and you can see whether they're actually polar by looking at it. I think that's about what I'm going to do tonight. Let me give you the guide that I talked about. I had a few more things, but this is a guide I put together for polar, non-polar molecules. And it's free. You don't have to do anything. You can just download it if you want. Let me see if I have a copy of it. Yeah, here it is. So this is what it looks like. It's got all the electronegativity stuff. It talks about the differences, the different values here. And it just gives you examples. Lots of practice, the answers, more practice down here, and some links. So grab that from the website there. You are welcome to do that. And Nishat, I do agree that 2D is easier for understanding initially, but if you want to start looking at polarity and the shape of the molecule, you really have to move to 3D. Chelating agents. Okay, that gets pretty advanced. I'd have to think about that there. Yeah. So do grab that guide, especially you, Hector, there, who have your test tomorrow. Make sure you get the guide up here. It's, like I say, you can just download it. I normally only give this to members, but it's great to see so many of everybody here this evening. And yeah, so that's a good question, Marlon. It does help with the Lewis structure somewhat. If you look at this here, you need to know that you have a carbon here, and then you can see the oxygen. It really doesn't show you the electrons, but but after you use it for a little while, you can see there's a carbon, it's bonded to an oxygen, and that can help you out. You could also go over here and look at it too and see if there's single or double bonds. So it does help with Lewis structures. So that is it for me this evening. Thank you everyone for joining. We have our record number of people here on the stream. That may be because I scheduled a day or two in advance. I don't know. I'll have to test that hypothesis there, do some statistical analysis. I'll get zero motivation to do the stats for me, I think. And everybody, you have a great evening. As always, this is Dr. B, and thanks for watching. Oh, Arya, I have to go. I have to go to bed. All right. Good night. It's night here. I'm going to bed. I will see you all next Tuesday. I probably won't be on Thursday. This Thursday I have to be somewhere. So probably next Tuesday I will be back. Take care, everyone.